بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is section 3.3 and it's about Gauss and Jordan elimination, solving systems of equations. So we will talk here about Gauss and Jordan elimination method, and we will start with systems with unique solutions. So systems with only one solutions. We know when we studied systems before that there are systems with one solution, there are systems with no solution, inconsistent systems, and there are systems with infinitely many solutions. Well, first thing to understand is to write the augmented matrix of the system. So whenever we have a system like this, okay, we write the coefficients of x in the first column, the coefficients of y in the second column, the coefficients of z in the third column. So for example, 3, -1, and -1, and the constant terms here in the augment in this place, okay. These are the constant terms. In the first row, you see the coefficients of the first equation, 1, 2, 3, 6. In the second row, you see the second equation. In the third row, 1, -1, -1, -4, you see the third equation. Of course, if you have systems of more than 3 by 3, you can do the same. You can find the augmented matrix similarly. This matrix is called the coefficient matrix. This matrix to the left is called the coefficient matrix. So for example here, write the augmented matrix for this system. Well, the augmented matrix would be 3, 1, 2. These are the coefficients of x. 2, -1, 3. These are the coefficients of y. -1, 2, -1, the coefficients of z. And 3, 4, 3, the constant terms. Write the coefficient matrix for the system. Well, the coefficient matrix would be the matrix to the left, 3, 1, 2, 2, -1, 3, -1, 2, -1. So it would be this matrix. This is the coefficient matrix. Now we can use matrices to solve systems of linear equations by performing some operations called elementary row operations. So elementary row operations, we use them to change matrices from matrices to equivalent matrices, or from systems equivalent to other systems. The three row operations are interchange two rows. We can interchange any row. For example, we can write R1, R2. This means we interchange row 1 with row 2. Add a multiple of one row to another row. For example, we can multiply row 1 by 2 and add that to row 2. This is the second operation. Multiply a row by a non-zero constant. So for example, I can multiply row 3 by half. Okay. These are the three operations we can use. To be systematic, I will use the second operation. This operation I always use to make zeros. Okay. The first one, I will always use it to make 1, and here to make 1. Okay. So try to use this method at the beginning. Use operation 1 and 3 to make 1, and operation 2 to make zeros. For example, we start with this. This is the augmented matrix of a system, and we will end by this matrix. So you see the coefficient matrix is changed to the identity matrix. Okay, the coefficient matrix is now the identity matrix, and the constant terms will be changed to these values. And immediately now we can see that this is x here. So the coefficient of x is 1. So x is -0.5, and also y here is 4, and this is the coefficient of z. Okay, this is so 1 z, 1 times z equals -0.5, and this would be the solution of the system. So if we can change this matrix, the augmented matrix, to this one, we will be able to immediately to solve the system, and we can do that using the row operations. So what would be our plan? Okay, let us start with this system. This is the augmented matrix of the system. What to do with this augmented matrix to change it to the required form? We need to 1 0 0 0 1 0 0 0 1, and what would happen here we don't know. Okay, so this will give you the steps you need to follow. First step, I'll go column by column. We usually here go column by column. So start with the first column. Look to the first column. This number must be 1. So the first step is to get 1 in row 1, column 1. This number must be 1. Okay. Second step, and how to make it 1? Remember how to make it 1? You use either operation 1 or operation 3. You interchange any two rows, or you multiply a row by a non-zero constant. So if this number is not 1 and there is a 1 below, you can interchange the two rows to get 1 in this place. Okay, so this is if there is no 1 below, and this is a 3, for example, you can divide row 1 by 3. So either you interchange with a row below, or you multiply by 1 over 3 or 1 over 2 or 1 over 5 to make it 1. So this is step 1. Step 2, now we need to make these numbers zeros using this one. Okay, using this one here, which we made in step 1. So how to make zeros? We use operation 2. We add a multiple of row 1 to row 2 and a multiple of row 1 to row 3, and we make them zeros. So the operations here we used is negative 2 times R1 plus R2. We multiply row 1 by negative 2 and add it to R2 and put the result here in row 2. So negative 2 times 1 plus 2 is 0. Negative 2 times 4 plus 5 is negative 3. Negative 2 times 3 plus 4 is negative 2. Negative 2 times 1 plus 4 is 2. So you use the calculator and you do this operation and you write the results here. Also, I'll multiply first row by negative 1 and add it to R3. So because this number is 2, you multiply by negative 2. This number is 1, you multiply row 1 by negative 1. And by this, you finished column 1. Now column 1 is 1, 0, 0 as we need. Now let us go to column 2. What do we need in column 2? First, you make 1. So first, I make this. This is step 3 now. This number, I make it 1. How do I make it 1? I interchange this row with the row with row 3, if there is 1 here, or I just multiply by 1 over 2 or 1 over 3 or so on. So here, now we are in this matrix. We need this number to be 1. This number below is not 1, so we divide by negative 3. So we multiply row 2 by negative 1 over 3, and we get 1 here in this place. So this is step 3. Now step 4, we use this one to make these numbers zeros. 4 and negative 7 now must be zeros, and by this we finish from row 2. So you see the process. Okay, you make 1 and then you use it to make zeros in the column, and the ones are these numbers in the main diagonal, because you need the identity matrix. Okay, so this is 1. I'll use it now to make this number 0 and this number 0. So how? Well, what do you have here? I have negative 7. So I will multiply row 2 by 7. Okay, 7, and add it to row 3. Okay, let me write it here, because I'm going to change row 3. So 7R2 plus R3. This will make this number 0 and will change the other numbers. This is 4, so I multiply row 2 by negative 4. So negative 4 row 2 plus R1. And I put the result here in row 1. And I will get now these values, new values. And now I finished from column 1 and column 2. Step 5, I go to column 3. This number, I have to make it 1. Now there is no row below this row. So here you cannot interchange in this step because there are no rows below. You always interchange with a row below this row. So I need to make it 1. So I will multiply by negative 3. Multiply row 3 by negative 3. You get 1 here. And this number would be 2. And now the last step is to use this one to make these numbers zeros. This is 2 over 3, so I will multiply row 3 by negative 2 over 3. And this is 1 over 3, so I will multiply row 3 by negative 1 over 3. And this would be the answer. And now I reached the last step. And I can say that x is 3, y is negative 2, z is 2, and that's just the answer. So let us see another example, a 4 by 4 example. This is the augmented matrix, first step, okay, writing the augmented matrix. And now we need to change the augmented matrix to the identity matrix 4 by 4. 4 by 4, so these numbers in the main diagonal, these numbers has to be, each one of them has to be 1. So I start with column 1. This number is already 1, so that's good. Now I need this one to change these numbers, these 3 numbers, to zeros. Each one of them is 1, so I multiply row 1 by negative 1 and add it to row 2 and add it to row 3 and add it to row 4. And this means I interchange row 2 with this, with the result of this operation. So I'll get to this matrix. And now I finished row 1. Column 1. Column 1 is what I need. Now this number must be 1. It is already 1. So I use it to make these numbers zeros. Well, these two numbers are zeros, so I need to make this number 0. It is 1, so I multiply negative 1 times row 2 plus R1, and I replace this with row 1. And now I finished from column 2. Now I go to column 3. This number has to be 1. So I do, and the number below is not 1. Okay, so I divide by 2 and I make it 1, or I multiply by half. Now it is 1, so I need to make these 3 numbers must be zeros. So this is negative 5. I multiply row 3 by 5 and add it to row 4. This is negative 1. I multiply row 3 by 1 and add it to row 2. This is 2. Row 1 is 2. So I multiply row 3 by negative 2 and add it to row 1. And now I finished the 3 columns. The next step, this number must be 1. So I multiply by negative 1 over 7. So now it is 1. And now I use it to make all of these numbers 3. This is zeros. This is negative 2. I multiply row 4 by 2 and add it to row 3. 3 R4 plus R2. Negative 7 R4 plus R1. This will give me this last matrix, and this is Gauss and Jordan method. Then X is 1, Y is negative 2, Z is 5, and let us call the he called them X1 up to X4, so let us use his notation. So X1 is 1, X2 is negative 2, X3 is 5, and X4 is 1. And that's the solution of this system. Let us now solve this system. I start by the augmented matrix. 3, 1, 2, 2, negative 1, 3. Coefficients of Z are negative 1, 2, and negative 1. And I write the constant terms. Okay, now let us work with column 1. This number has to be 1. How can I change to 1? Either I interchange or divide by 3. Luckily, the second row, this is 1. So I will just interchange row 1 with R2. So row 2 would be in the position of row 1, and row 1 would be in the position of row 2. And row 3 remains without any change. Okay, now I finished from this number. It is now 1. I use it to make these numbers zeros. Well, this is 3, so I multiply row 1 by negative 3 and add it to row 2. This is 2, so I multiply row 1 by negative 2 and add it to row 3. And now I get a new matrix. The first row is not changing, but now this operation will change row 2. So let us do it. Negative 3 times 1 plus 3 is 0. Negative 3 times negative 1 plus 2 is 5. Negative 3 times 2 is negative 6 plus minus 1 is negative 7. Negative 3 times 4, negative 12 plus 3, negative 9. Now row 3. Negative 2 plus 1 and negative 2 times 1 plus 2 is 0. Negative 2 times negative 1 is 2 plus 3, that's 5. Negative 2 times 2 is negative 4 plus negative 1, that's negative 5. Negative 2 times 4 is negative 8 plus 0, that's negative 8. And now I finished dealing with column 1. Now I need to go to column 2. I need this number to be 1. So how to make it 1? If I divide by 5, I cannot interchange with row 3 because there is no 1 here. Okay, so if I divide by 5, I will get here negative 7 over 5, negative 9 over 5, and I don't want to deal with fractions unless it's a must. So now if I well, I think I made a mistake here. Yeah, this is not 0, this is a 3. So negative 2 times 4, this is 3. Also here, this number is 3. So negative 2 times 4, negative 8 plus 3, that's negative 5, not negative 8. So if you look to row 3, if you divide row 3 by 5, then you get 1 here. You can do that if you like. I can multiply row 3 by 1 over 5. And why is that? To get 1 in the third row, second column. So negative 5 over 5 is negative 1, and here negative 1. And now I can interchange row 2 and row 3 and get 1 in the position I need. So row 2, row 1 will not change. Now row 3 will be in position of row 2, and row 2 will be in position of row 3. And now I have 1 here. So I use it to make these numbers zeros. Well, this number is negative 1. So I multiply row 2 by 1 and add it to row 1. This number is 5. So I multiply row 2 by negative 5 and add it to row 3. So the new matrix would be The second row is not going to change because we are using it now to make zeros. And now R2 plus R1, so 0 plus 1, 1 minus 1 is 0, negative 1 plus 2 is 1, negative 1 plus 4 is 3. Negative 5 times 0 plus 0, that's 0. So you notice that when this is 0 and you are using this row to make ones, the numbers in the column will not change. The numbers in the first column are not going to be changed if you follow this method, the systematic method which we are using. Negative 5 times 1 plus 5, that's 0. Negative 5 times negative 1 is 5, plus negative 7, that's negative 2. Negative 5 times negative 1 is 5, plus negative 9, that's negative 4. And now I finished dealing with column 2 and I need this number to be 0. I have no rows below, so I will just multiply row 3 by negative 2. So row 1, no change. Row 2, no change. And row 3, negative 2 over negative 2 is 1. Negative 4 over negative 2 is 2. And now I need this number and this number to be zeros. And this is the last step. This number is negative 1, so I multiply row 3 by 1 and add it to row 2. This number is 1, so I multiply row 3 by negative 1 and add it to row 1. And now the last row, no change. And let us change row 1. See, these are zeros, so nothing will happen here if you do these operations. Now R3 plus R2, 1 plus minus 1 is 0, 2 minus 1 is 1. And negative R3 plus R1, negative 1 plus 1 is 0, negative 2 plus 3 is 1. So the answer would be X is 1, Y is 1, and Z is 2. And this is the answer, the solution of the system. Let us now talk about systems of non-unique solutions. We can have systems of no solutions or systems of infinitely many solutions. So what to do? In this case, when you try to use Gauss and Jordan elimination, you will not, the original matrix will not be reduced to the identity matrix. You will not be able to reduce the matrix to the identity matrix. Instead, you will reduce it to what we called the reduced form, okay? The reduced form of a matrix. So what is the reduced form of a matrix? Uh, it satisfies four conditions. You need to understand them. The first, non-zero element in each row is 1. Of course, these conditions are also satisfied in the identity matrix. The identity matrix satisfies them. So you go each row, the first non-zero element should be 1. So for example, here, the first row, this is the first non-zero element, it is 1. In the second row, this is the first non-zero element, it is 1. In the third row, all elements are zeros, so uh, the first condition is satisfied. Okay, it's that easy. Okay, look here, for example. Look to this matrix in the middle. Now, the first element is the first non-zero element in the first row is 1. That's good. But the first non-zero element in row 2 is not 1. So this matrix is not in the reduced form because the first non-zero element of row 2 is not 1. It has to be 1. So you have to divide by 2 here to make it 1. All right. What is the second condition? Any column contains a first non-zero element for some row has to have zeros everywhere else. Or if you want, you can say the first non-zero element in each row is 1 and all the elements above and below are zeros. All right. So I prefer to understand it like this. So 2, you can find it from here because you need to go to first non-zero element in each row, and now you look above and below, and all other numbers in the column should be zeros. So for example, here, the first non-zero element in the first row is 1. All the other numbers must be zeros in the column. So this is 0, this is 0, so that's good. Now, second row, you go row by row, okay? Second row, where is the first non-zero element? This one. This is the first non-zero element. It is 1, that's good. Now, the numbers above and below should be zeros, so this matrix satisfies the first and the second condition. Is that clear? Let us try here, this one. The first non-zero element in the first row is 1, and below zeros. That's good. Now, the second row, you go row by row. The second row, the first non-zero element in the second row is 1. That's good. But this number is 0, but this number is not 0. That's not good. This number has to be 0. Okay, so this matrix is not in the reduced form. I hope that's clear. So first and two conditions could be the first non-zero element in each row is 1, and all the elements above and below in the same column should be zeros. Now, the third condition, the first non-zero element of each row is to the right of the first non-zero element of every row above it. Okay, so this means that the one in the second row is to the right of the one in the first row. Okay, for example, here, this one is to the right of this one, and this one is to the right of this one. So this matrix satisfies condition 2. Now look here to this matrix. This one in the second row is not to the right of this one, so this matrix is not in the reduced form. I hope that this also condition is clear. All rows containing zeros are grouped together below the rows containing non-zero enters. So the last, the zero rows, if there is a row all zeros, it has to be at the end, okay, at the bottom. So this is okay, this is okay, this is okay, because and also here, this is okay, this condition is okay here, this condition is okay here, but there are other conditions not satisfied, and that's why these three matrices are not in reduced form, while these matrices are in reduced form. Okay, so we will change now matrix with non-unique solutions to the reduced form, and let us see here. Of course, this is x2, and this is x2. All right. So let us write the augmented matrix. This is the augmented matrix. Now, this number has to be 1. It is 1. So we use it to make all of these numbers zeros. This is already 0. I need this to be 0, and I need this to be 0. This is 1, so negative 1 R1 plus R3. This is 2, so negative 2 R1 plus R4. And now I finished from column 1, and all the numbers are zeros. 1 and zeros below. Good. Now I move to the second row. Okay. This number has to be 1. Good. It is already 1. So I use it. I use this one to make these numbers zeros. This one, this one, this one has to be zeros. Okay. How to make them zeros? Well, this is 1. So I multiply row 2 by negative 1. Negative 1 row 2 plus row 1. This is negative 1, so row 2 plus row 3. This is negative 3, so 3 row 2 plus row 4. And now I finished column 1 and column 2. Now I go to row 3. This number has to be 1. Well, it is 0. So if I can make it 1 if this number below is 1. So I can interchange the two rows. But this number below is not 1. So I cannot make this number 1. This number cannot be made 1 unless I change change everything I did before. I lose everything I did before. And I cannot interchange row 2 with row 3 here because the column 2 will be changed. Okay, so to change this number to 1, you have one choice: interchange with row 4. If row 4 is 0, you cannot change this number to 1. So that's it. What to do? You continue with row 3. You continue in the same row, row 3, and you make this number 1 instead of this one now. Okay, this is 1 already. That's good. Now I make it to use these numbers in the column, in the same column, zeros. So this is negative 2, so 2R3 plus R4. This is 1, so negative R3 plus R2. We'll make these numbers zeros. And now column 1, column 2, and column 4 are excellent, and these are zeros. So this is the reduced form. This is the reduced form. If you check the four conditions, in the first row, this number is 1. The non-zero, the first non-zero number is 1, and every other number in the column is 0. That's good. In the second row, the first non-zero number is 1, and all the numbers below and above are zeros. In the third row, the first non-zero number is 1, and the numbers above and below are zeros. So condition 1 and 2 are satisfied. Now this one is to the right of this one is to the right of this one. So condition 3 is satisfied. Row 0, row with all zeros, is at the end of the matrix, the fourth row. So condition 4 is satisfied. And now we are in the reduced form. These four conditions are satisfied and we are in the reduced form. So let us write now the equation to solve the system. So we have x1, x2, x3, and x4. So these are the coefficients of x1, x2, x3, and x4. So what do we have? We have x1 times 1 minus 2 x3 equals 2. This is the first equation. And this one is the coefficient of x2. So I have x2 plus x3 equals to negative 3. And the third row will give me x4 equals to 4. And the last row will give me 0 equals to 0. When you have 0 equals to 0, this means that the system has infinitely many solutions. If it happens that this is 0 and here there is a number 1 or 2 or 3 or 4 or any number other than 0, then 0 will be equal to a number, and this means that there is no solution of the system. This is not correct, so there will be no solution of the system. Here, infinitely many solutions. Infinitely many solutions means you will lose one of the variables. Okay, one of the variables are lost here because one of the equations, one of the equations are lost. So you cannot find a unique solution. So how to write the solutions of this system? You solve the first equation for x1. So x1 would be 2x3 plus 2. This is the solution. This is x1. And x2 you solve it, the equation 2 you solve it for x2. So it would be negative x3 minus 3. And x4 is 4. Okay, what is left? X3 is left. I have x1, x2, x4, x3 is left. So what is x3? X3 could be any real number, free variable. It could be any real number. So this will give you the solution of the system. Infinitely many solutions. If you want to find one solution of these infinitely many solutions, you can choose x3 to be any number. So for example, if I choose x3 0, okay, what would happen? x1 would be 2, x2 would be negative 3, and x4 is always 4, and x3 would be 0. So this would be the solution if x3 is 0. If x3 is 1, you can find another solution. If x3 is 2, you can find another solution. So there are infinitely many solutions. If x3 is 1, 2 times 1 plus 2, x1 would be 4, x2 would be negative 1 minus 3 is negative 4, x4 is always 4, and x3 in this case is 1, and so on. Another example, system with no solution. Let us solve this system. Let me write the augmented matrix. 1, 3, 2, 2, 1, negative 1. Coefficients of z are negative z, 0, and 1. There is no z in the second equation. 3, 4, and 2. Well, this number has to be 1. It is 1. Good. Now I use it to make these numbers zeros. Okay, 3 and 2 should be zeros. So this is a 3. So I multiply row 1 by negative 3 and add it to row 2. This is 2. So I multiply row 1 by negative 2 and add it to row 3. Okay. Row 1 is not changing. Now, negative 3 times 1 plus 3 is 0. Negative 3 times 2, negative 6 plus 1 is negative 5. Negative 3 times negative 1 is 3 plus 0, 3. Negative 3 times 3, negative 9 plus 4, negative 5. That's row 2. Row 3. Negative 2 times 1 plus 2, 0. Negative 2 times 2, negative 4 plus minus 1, that's negative 5. Negative 2 times negative 1, 3 plus 1, that's 3. Negative 2 times 3, negative 6 plus 2, that's negative 4. And now I can change this number to 1. So 1 over negative 5 times R2, because the number below is not 1. Of course, here, if you understand, and after a while, you will notice from here immediately that this system has no solution. And the reason of that, because we have here negative 5, 3, negative 5, 3, while here are two different numbers. But let me continue to the Gauss and Jordan, to the reduced form. Let us write it in the reduced form. So 1, 2, negative 1, 3, and 0. Negative 5 over negative 5 is 1. This is 3 over negative 5. And this is negative 5 over negative 5, also 1. And row 3 would be 0, negative 5, 3, negative 4. Now I need to use this number, which is 1, to make 2 and negative 5 zeros. This is 2, so I will multiply row 2 by negative 2 plus R plus row 1, and 5 R2 plus R3. The new matrix would be this row is not changing, second row. Okay, and 0, 1, 0 will not change. Okay, negative 2 plus 2 is 0. Negative 2 times 3 over 5, that's 6 over 5. Minus 1, that's 1 over 5. You can use the calculator easily. Negative 2 times 1, negative 2, plus 3, 1. Okay, the third row. 5 times 2 is 10. 5 times 1, we are multiplying our row 2 by 5. 5 times 1, 5, minus 5, 0. 5 times 3 over negative 5 is negative 3, plus 3, that's 0. 5 times 1 is 5, plus minus 4 is 1. And now you can see that this is the reduced form. This is the reduced form. Let us check the four conditions. The first non-zero element in the first row is 1. That's good. All the numbers below is 0. In the second row, the first non-zero element is 1. The numbers above and below are zeros. That's good. And there is no non-zero element here in the third row. Of course, we are talking in the coefficient matrix. Okay, these four conditions are applied only in the coefficient matrix. So the first and the second conditions are satisfied. The third condition, this one is to the right of this one, that's good. The fourth condition, this row has all zeros. It is the last row, so that's excellent. Okay, So finished. This is in the reduced form. This is in the reduced form. So I must now get a solution. Well, the last equation I can write. I can write the equations if I want. The first equation is x plus 1 over 5 z is 1 and y minus 3 over 5 z is 1, and the last equation gives 0 times z, that times x times y times z, 0 equals 1. This is not possible. Okay, 0 equals 1 is impossible. So the solution set is phi, and this system has no solution. So this is the summary. When we reduce the augmented matrix, when we write the augmented matrix into the reduced form, if the system has unique solution, we will be able to write the coefficient matrix as identity matrix. If the system has no solution, then we will not be able to write the coefficient matrix in the identity matrix, and we will get 0 in the coefficient matrix in the last row and non-zero entry in the here, 0 and a number here in the constant term. So this will give you no solution because 0 cannot be equal to 3. While in infinitely many solutions, you will have 0 and 0. Okay, 0, 0. This will give you infinitely many solutions. And there will be a non-lead variable, a variable which is non-lead. Okay, so you solve for lead variables. What are the lead variables? Like here in this question, the lead variables are x1, x2, x1 and x2. You solve for the lead variables. The coefficient of the lead variables is 1. Okay, lead variables have coefficient 1. Checkpoint for each system of equations, the reduced form of the augmented matrix is given. See here, the reduced form is the identity matrix. So here we have a unique solution. Give the solution. The solution would be x is 100, y is negative 80, and z is 110. All right. While here, you see that this is the reduced form. The reduced form is not an identity matrix, and we have 0 equals to 0. Well, 0 equals to 0, we will have infinitely many solutions here. So let me write the equations. X minus z equals to 8, and y minus 5z equals to negative 2, and zeros equals to zeros. The lead variables here are x and y. So I solve for x. So x would be z plus 8. Y would be 5z minus 2. Okay. And the non-lead variable is z here. Z is the non-lead or the free variable. So z could be any real number. Okay. Give the solution of the system. This is the solution of this system. And if you want, you can uh, give an example of these infinitely many solutions. Here, I can write the system x minus 1 over 3, z equals 0, and y minus 5 over z equals 0, and 0 equals 1. This is not possible, so the system has no solution. This is the end of this system, this section, and see you in the exercises.